is basically the fact that many pharmaceutical industries produce a lot of effluents and liquid effluents, predominantly containing water and dissolved APIs in that. So, in general, those APIs cause a lot of health hazards to people, to humans, and human or animals, or in general, the biodiversity. So, we need to treat them before releasing it to water bodies or to the groundwater. In fact, even small amount of amoxicillin can cause the development of antibiotic-resistant bacteria in humans, and that is not so favorable, and that is about this. So we need to treat them. So this was the basic problem statement, and yeah, our target is to achieve more than 90% efficiency in this. So next. So we are proposing the microalgae treatment for drug degradation. So why microalgae? Since it because microalgae have the metabolic pathways that through which they can break down the drugs. In this, we have chosen amoxicillin specifically based on your feedback in our midterm report to stick to specific drug and do its treatment. So choosing this microalgae because of its metabolism that can break it. And again, to make it sustainable, since the fuel here required is only the sunlight, so it makes it sustainable solution. So next is out of those microalgae, why specifically chlorella for amoxicillin? So it has been already studied that chlorella can quite nicely break down amoxicillin and due to the presence of the cytochrome P450 enzyme in chlorella. So this helps it to break down this amoxicillin. And again, after that, chlorella are also seen to survive in very high concentrations of amoxicillin, so which is a favorable situation. And again, chlorella are very quick at growth, and they are kind of rough and tough in terms of their adaptability to the environment. Next.
So now we are proposing a membrane photobioreactor. So the first question arises why we are using membrane specifically here. So we have observed that microalgae has a very poor gravity settling ability. Means it does not settle down on a due to its gravity. So it's remain in the suspended form. So in order to have that in order to retain that microalgae within the medium, we should use a membrane which would not allow the microalgae to pass through the pores of the to pass along with the treated effluent. So we are using a membrane for membrane for separating the microalgae with the treated effluent. So microalgae we using is the cholera, which is of the order which has a diameter of the order of 2 to 10 micrometers, and we are proposing a ceramic ultrafiltration. So ultrafiltration has a pore range of between 0.01 to zero point 0.1 micrometers of pore diameter. So we should not allow the microalgae to pass through it. So that's the beneficial of using membrane. So the membrane allows a higher retention time of the microalgae, which will increase the efficiency of the process and would result in more treatment of the drug. So now we need to select the membrane. So we have two membranes. One is the ceramic and another was the polymer membrane. The properties that a membrane should provide are durability and stability. That is, the membrane should withstand high temperature. Membrane should withstand high temperature stream, which would be beneficial while dealing drugs present in hot wastewater stream or when cleaning of membrane is done at an elevated temperature. Also, it should be chemically resistive towards corrosive chemicals or strong acids and strong base alkalis. Over time, there could be some cases where the effluent water input to the system could be of variable chemical composition. Also, the property we should handle a large, high amount of flux rate without losing the efficiency of the membrane for the scalability purpose. And also, we should one of the main reasons to consider is the fouling resistance. Over the time, there will be deposition of particles on the membrane surface. This deposition can get increased if the surface is rough. So we should stick to smooth surfaces and avoid the surfaces which might have grooves on it. So these are the main things we should consider before selecting the membrane. So we have ceramic membrane and polymeric membrane. From durability standpoint, ceramic membrane outperforms the polymeric membrane. It can handle a large temperature and can also handle a very basic and acidic compounds. Similarly, mechanical strength. Since we are using porous membrane, the membranes are porous in nature, so they are pressure driven. So there will be a transmembrane pressure between the permeate side and the retentive side, which will drive the flow of the permeate through the membrane. So that in case of ultrafiltration, it should be between 1 to 10 bar. So which could be easily done in the ceramic membrane, and in case of the polymeric membrane, it is about 2 to 5 bar, and which also increases when this pressure difference increases when the fouling resistance increases. So in terms of mechanical strength, ceramic membrane has more strength. And I as discussed earlier, it can handle highly acidic and basic solutions. The ceramic, while this can handle moderate and limited range of the basic and acidic solution. And ceramic membrane, since ceramics are made of metals, their surface are hydrophilic in nature, and the medium, the chlorella, which is metabolizing, produces carbohydrates and lipids which are hydrophobic in nature. So hydrophobic elements can't get fouled easily on the hydrophilic surface because they repel each other. So this is an added advantage in case of ceramic membranes. But while polymeric membranes are made of polymers which are too hydrophobic in nature, so hydrophobic fouling materials can easily get deposited on the hydrophobic surface of the polymeric membrane. So there could be easily deposition of fouling materials in this case. High selectivity, yes, the pores are very small and high reflux rates can be handled, but here the performance can drop over the time. But one disadvantage of ceramic membrane is that it is slightly more costlier, around 10 times more costlier than the polymeric membrane used in industrial appliance. While polymeric membranes are cheaper comparatively and are used for several are being used in industry for several years. But ceramic membrane can last longer, while this can last for only 1 to 3 years, while it can last 10 years. And overall cost and decreases in case of ceramic membranes, but in polymeric membranes it increases due to it is not so long lasting. So now the ceramic we are now and finalized that we will be using ceramic membranes. Out of the ceramic membrane, the base material which will be using is aluminum Al2O3. We have other options of ceramic material like zirconium dioxide, silicon carbide. All those are highly expensive, and alumina is relatively cheaper than others. And with this cheaper property, it also provides high mechanical strength and offers good resistance to chemicals. So it is advisable to use alumina as the base material for the ceramic membrane. So now we need to compare the photobioreactor membrane photobioreactor vessel material, the vessel in which we are conducting we are degrading our drug. So we have option of polypropylene plus polyethylene combined as a vessel material, glass as a vessel material, and conventional steel as a that the conventional stainless steel as a material. So out of this, we have chosen polypropylene and polyethylene. Because in the base material, the most important parameter is we should have high maximum we should have high irradiation. The irradiation from the source should be taken by it. So stainless steel is generally opaque and it discarded. Glass is transparent and used. While polypropylene and polyethylene combined is a semi-transparent translucent type and it can absorb 70 to 80%, but not as much as glass. But with glass, we have some more challenges like it is heavy and we should be very careful while handling it. While polypropylene it is lightweight and it can't be installed anywhere. Similarly, the cost is affordable for this, while the glass is very expensive. So we should, in terms of durability, too, glass is brittle, but polypropylene and polyethylene are resistant to fatigue and stress and can last for several years with proper care. So based on this, we are using a polypropylene and polyethylene. I accept that while glass and stainless steel have their advantages in their specific application, but polypropylene and polyethylene made vessel offer a compelling combination of cost effectiveness, durability, and operational stability for membrane photobioreactor design. They can be of particular advantages in large scale setup where budget and flexibility are essential consideration before design. So that's all the polypropylene, the base material for the photobioreactor.
Hi, I'm Aryan. I'll continue from here. So our proposed reactor design is we are proposing to use a multinuclear vertical bubble column reactor. So I will just go through overview. So yeah, our reactor design multinuclear vertical bubble column reactor where we can use the number of any number of tubes. I mean not any, but we can find the optimal number of tubes. But for now we are giving it as taking it as 4 vertical tubes arranged in a rectangular configuration, which will allow efficient mass transfer and enhance interaction between wastewater and microalgae. The reason behind this is if we are so think like this way, instead of 4 tubes, if we are using only 1 tube, then of course we have to use the tube with high cross section if we want to instead of 40, if we're using 1 tube, then if we want to use the same amount of algae in that tube, then we have to use the large diameter tube. So the sunlight is also important in our process because it's photobioreactor. So the sunlight will reach to outer microalgae, but the microalgae which are close to the center of the tube, which are inside the tube, the sunlight reaching to them will have lesser intensity or less illuminance. But instead of that, if we are using multiple tubes with smaller diameter, then the illuminance reaching towards the center will be higher instead of using just one large tube of higher diameter. So that's why we are proposing to use tubular reactor instead of just a single tube. Just you can say we are just increasing the length of that configuration. Uh, actually, we are just passing it through multiple passes, like instead of putting it in single configuration. So now reactor configuration, the structure. The reactor consists of 4 vertical tubes of diameter 15 centimeter and uh, so reactor configuration, structure. Okay, I will quickly go through all of this. So structure, we are using the diameter of 15 centimeter. So here we are proposing the structure as a abstract so that we can do some calculations from which we will get the idea about flow rate, etc. That's why we are taking some specific values of diameter, height, etc. In real life, we have for applying it in industrial purpose of wastewater treatment, we have to check according to our need, according to our flow rate, the time in which we have to separate or the setup area which we have. So according to that, we have to find the structure, exact diameter, height, exact area of the tubes. But for now, let's take them as example. So the diameter is 15 centimeter, height is 3 meters for the tubes, and inlet is wastewater entering, and also the we have to give the air pressurized air from the bottom of the columns because the oxygen is necessary for the microalgae. That's why air is necessary. And in outlet, there will be, of course, the cleaned water from which we are removing the pharmaceuticals and breaking them in simple harmless compound molecules. Now the operational flow, water flow, gas supply. So there are two flows. Basically, the water flow is wastewater flows through the first tube, and then it travels down through them and sequentially passes through another tubes. Uh, Actually, there is some confusing language, but yeah, I will explain. So it is basically passing through all of the tubes simultaneously, and it is flowing in the parallel fashion. So I will I mean, for 2 3 slides, I will come to this image. But for now, you can see that like wastewater is coming and it is moving through all the four tubes simultaneously in the parallel fashion. So wastewater is coming from here and going here, 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 and here in parallel way, and then it is again coming back to bottom and going through this ceramic ultrafiltration membrane, and the air is entering from bottom pressure is there, which is supplying oxygen. And that's why there you can see these bubbles, which are basically air bubbles, these oxygen bubbles. And here you can say that it's counter flow, like wastewater is coming from top and bubbles air is coming from bottom. So here it is the counter flow, and this arrangement of the counter flow and supplying air from the bottom. So this is basically bubble column, and here we are using four bubble columns in parallel setup. So each column is a bubble column, and we are using them in parallel setup. So the advantage of using bubble column is it improves the mass transfer. So like here you can see there will be many small bubbles. So as the number of bubbles are I mean, there are many number of bubbles. As the number of bubbles is high, the surface area will be higher. Like I mean, as many number of bubbles, the surface area will be high. I mean, as higher the number of bubbles, the surface area will be more. So that's why there will be more surface area for the mass transfer, and the mass transfer will be efficient between the from oxygen. I mean, from these bubbles. So mass transfer of oxygen basically. So from these, it will move to the wastewater. I mean, to the algae who need it, and also the uh, if we don't use this bubble column, then also we have another option of using the grinding technique. I mean, sorry, using some fan. I mean, like agitator, you can say. So we can use some agitator kind of thing, and we can supply the air, and we can do agitation to mix the algae with wastewater uniformly. But the second advantage of bubble column is, I mean, it is improving the oxygen mixing in the wastewater. But with that, due to this drag, like air pressurized air is coming from bottom, like right. So it is applying some force. So there are maybe the algae are some algae are coming with water at the bottom. So water is flowing from top to the bottom. So with that water, maybe some algae, microalgae chlorella, which were initially here, maybe they will also come to the bottom due to the drag of this water. And here also they all will come to the bottom. But as we are supplying the pressurized air from bottom, it will apply force on them, and it will again help to move them up and to mix them uniformly with this. If there is no air, then you can imagine all the algae will accumulate at some one place and they will not mix in this wastewater uniformly. But yeah, that problem is solved by this pressurized air, which is basically helping to mix the chlorella algae uniformly in these columns. But yeah, as I said, we can also use another technique like agitation. We can use for uniform mixing. But then there is one problem. Like for agitation, we will need energy, right? So I mean, we have to supply extra amount of energy, but we want our solution to be sustainable. That's why we are using the natural air, and to increase the pressure of air, the energy needed is not much as compared to agitation. For agitation, we will require significantly high amount of energy as compared to supplying air, pressure air to this column. So yeah, the using air from bottom, like using the logic of bubble column is the sustainable way to solve the problem of uniform mixing of algae in the wastewater. That is the second first thing. The second thing is why we are using the four columns in parallel. So as I said earlier, also if we use only one column, then there will be higher diameter. So here from here you can imagine instead of four, let's say we are combining all of these four into a single column. Then you can imagine there will be higher diameter for the same flow rate, and as there will be higher diameter, then the sunlight going to the middle, I mean, the microalgae which are present towards the center will be lesser intensive and lesser luminous. But instead of that, if we are using this such kind of multiple tubes, then the sunlight will be nearly uniform. The sunlight intensity will be nearly uniform. I mean, okay, even though if it is not uniform, then it will be better than a single column. The sunlight intensity reaching towards the middle algae which are close to the central line of these tubes. So that's the advantage of using multiple tubes in parallel fashion. And yeah, here is the counter flow. The advantage of counter flow is it is better. I mean, efficiently mixing the oxygen and microalgae. So we can also use the parallel flow, but then it won't help to mix the microalgae. Like if air is coming from the top only, then air will also force the microalgae to go with the water. So that will not be a good way. And also the oxygen mixing will not be that good in parallel. So that is why we are using counter current. And also the sunlight. The one more advantage is if we are as we are using multiple tubes, the area exposed to sunlight will be higher. So instead of single column, if we are using multiple column, then the area surface area of multiple tubes is greater than the single column. So that's why the area exposed to sunlight will also be higher, and that is also the one more advantage you can say. And in all these columns, microalga chlorella sp is present, and from here the water is going like this in these four columns simultaneously, and these bubbles are oxygen coming in this. So now here you can see the ceramic ultrafiltration membrane. So the necessity of this membrane is to retain this microalga. Like if we do not put this membrane, then microalga, even though there is air, but still the microalga some microalga still may go with the water, and if this membrane is not there, they will directly go in the outlet, right? So that's why we are putting this membrane here so that it will avoid microalga to go with water. And if the microalga is collecting here, then of course as the air is forcing them up, then they will maybe avoid it to go further. So maybe they will be stopped here, and air will force them to again go up, and then they will move in this fashion. So they will remain in this setup only, and it is basically increasing the hydraulic retention time of those microalgae, which basically means the time for which they are remaining in our reactor. Okay, and then after this, and this is a ultrafiltration membrane with very small walls. So we has already explained the details about it. And then after coming, the water is coming out of it. This is basically purified water, but it is around 85% pharmaceuticals are recovered from it. But then we can further do the bacterial treatment using wetland sediment or activated cells. We can use one of them, which increases this recovery of pharmaceuticals up to 99% recovery efficiency. So yeah, I mean, it is removing almost all the pharmaceuticals, or you can say breaking down them in simple knowledge, but almost all the pharmaceuticals. And then here we are getting the treated outlet water, which will be almost 99% free from the pharmaceuticals. So that is what all explained in this theory. So here I also this water flow rate filtration system, membrane filter system. So that is what explained here, flow rate, etc. So biomass retention and scalability, the reactor design. As you can see, we can easily scale such design, right? And this kind of reactors are already in use for different processes. So microbioreactor also we can easily scale up. Just we have to think about the microalgae chlorella, I mean, how we can get more higher amount of them in lesser cost, etc. So yeah, I will quickly go through reactor dimensions. So as I said, these are we have taken this dimension, but yeah, in the real time we may take some different dimension. These are you can take it as an example. So 15 centimeter diameter, 4 tubes, and generally as per our search, the industrial application diameter is generally 10 to 20 centimeters. So that's why we are taking 15 centimeters, and each tube typically ranges from 2 to 3 meters for good contact time. So that's why we are taking here. Uh, yeah, 3 meters. So height is 3 meters. That's all. So volume calculation will be pi d by 2, and basically pi. Sorry, area calculation will be pi square. Area of cross section. So this is the value of that, and what our volume will be simply area into height, and height is 3 meters. So this is our volume. It is around 53 liters. So 53 liters is for 1 tube, and we have the 4 tubes. So the total volume which is flowing at the same time will be 212 liters. So around 200 liters you can say. And then now we will calculate HRT, hydraulic retention time. How much time? Sorry, not calculating actually. We are assuming it around 12 hours because in the research paper they have done this experiment in a small scale in laboratory scale, and they have found that HRT is around 12 hours for applying this ceramic ultrafiltration membrane. So we are taking that only. And using HRT, we can find the volumetric flow rate using volume by time. So by volume by time, this will be our volumetric flow rate of you can say because this time is positive. And then this is the liquid volume. I mean, this is basically also a wastewater volume, so that's why it is liquid volume. And airflow is now the second important thing. So airflow is also generally in bubble columns. Reactor 1 to 2 liter of air per liter liquid per minute is taken. So we will take again average of them like 1.5 liter per minute per liter of solution, where in our case the solution is wastewater. So and it is 212 liters. So we will multiply 1.5 into 212. So that will be 318 liter per minute. So this is our airflow, and which is basically 5.31 liter per second. So now let's go through the operating conditions quickly. So we are using microalga chlorella sp for this micro membrane bioreactor process. Temperature required is around 25 degrees Celsius. These all values are as per the research done by the scientists mentioned in that research paper. So you can see as the temperature is 25 degrees Celsius, we can operate this process at ambient conditions only. And illumination required is 2000 lux, which is I mean this is the quantity of luminous, which is constant. This is again as per research paper. But yeah, in research paper mentioned they have used the light source artificially to provide the illuminance. But again, we want to make the sustainable solution. So what will we do? Instead of light source, we are providing this illuminance directly using sunlight. But we have to check whether the sunlight illuminance is greater than this value or not. So we checked it. So these are the values for that. The reference is from Wikipedia. So the illuminance of sunlight is 10,000 to 25,000 for the full daylight. I mean, we are not putting our reactor directly under the sun, but the sunlight is still come if we are standing below some tree. Not tree actually, but we are not directly exposed to sunlight. But in that case, this will be luminous. And if we are putting the reactor directly without any cover or without a small shadow, etc., then this will be luminous. So which is very hard. So as high luminous, the better will be our performance. So we can definitely use the sunlight, which is basically the sustainable solution. And we can also the control. I mean, even if the optimal condition to operate this microalgae is not such a high luminance, then we can definitely control it by putting some shade on this so that we will get the shadow from above about the reactor, and we can take the sunlight only from the side walls. That will decrease the luminance because if we are putting the shade, then this luminance will further decrease, and we can make it close to 2000 or let's say 2000 to 5000. So that's possible. But yeah, we don't need to use the artificial luminous source because that is consuming energy, which is not the sustainable approach. Now it is evident from the above values, yeah, as I said this. So reactor value, our is MTBR, membrane photobioreactor, reactor membrane time is submerged ceramic ultrafiltration membrane, and our flow rate was this as I have shown on this slide, 4.9 meter per second. And typical membrane, just a minute. Typical membrane. Yeah, so typical membrane plus is J. So membrane plus basically we want to find per unit area how much there is flow rate. So the typical membrane plus for ultrafiltration is generally taken as 100 to 10 to 100 liter per meter square hour, and conservative plus let's assume it as 10. I mean, we can assume any value between this. Let's assume is smaller value because our diameter etc. is smaller. So let's assume 20 liter per meter square hour for our setup, and from that we can calculate the area needed for this membrane, for this ultrafiltration membrane, this area. So we can calculate is using Q by J, and we are getting it as 882 meters square around. So high area, which is obvious because these are 4 Qs, right? So this area should be combined and greater than the combined area. I mean, around not always greater than, but around that. And membrane pore size is 0.1 micrometer because as explained by Somik already, because the microalga chlorella size varies from 1 to 10 micrometer. So membrane pore size should be lesser than that. And as this is the general size of the membrane, we are taking that. And the reason of putting it smaller is we want to retain the microalga chlorella in reactor, and we want to avoid them to pass with water. That's why we are putting it smaller than their actual size, and it's quite smaller than 1, also 1 to 10. So yeah, it will definitely do its fulfill its purpose. And hydraulic retention times 12 hours. Okay. So now proposed reactor design is giving 85.6 plus minus 3.8% removal efficiency of amoxicillin, and our target was 80% plus. Is satisfying that. And after that, we are also doing the subsequent bacterial treatment here. You can see, and it is further removing this efficiency to directly 99% plus. So our process is basically microalgal bacterial process. So first microalgal, that is chlorella sp treatment, followed by bacterial, which is basically either interacts tidal wetland sediment or activated cell. We can use any one of them, which can actually simultaneously 99% plus recovery. So the increase in efficiency is attributed to synergistic effect. I mean the combined effect of microalgae and bacteria. And microalgae first reduce the concentration of ANX and organic matter in wastewater, but after that subsequently the bacteria further process the partial treated wastewater, which will lead to higher pollutant removal rates, and which will lead to more pure water. Okay. How many can this?
The normalized, here we have plotted the normalized concentration of amoxicillin, the drug which we are degrading with time. So we can see when the LD is high, it is not dead or it is fully functioning or metabolizing. The concentration goes down very quickly. the green dots. While when it is dead, the most probable case is due to adsorption on its surface, the somewhat concentration drops. But when self-decomposition of amoxicillin, which could happen due to sunlight, which we are illuminating through the reactor, so which also leads to decrease in somewhat concentration of amoxicillin in the water. Another trend we can see is that for the same amoxicillin concentration, for the different amoxicillin concentration and having the same algae concentration, the cells of algae within the bioreactor, the amoxicillin degradation with degradation of lesser amoxicillin is more efficient than the amoxicillin with higher concentration for the same algae concentration, which is evident from green dots.
Okay, so here is the AI visualization of our design. So just to, I mean, just for the imagination, how will it look in real time? So you can see this picture. So multiple tubes and air supply with algae, and sunlight is coming from the top. Here you maybe you can pause the video and create in detail. And also this is the here we are using, I think, more than around 8 tubes we are using. So we can increase the number of tubes, as I said. If our flow rate is high, then we should use actually higher number of tubes to gauge that flow rate. And yeah, references, these two images are generated using Dali, text to image model by OpenAI. So yeah, we basically use the generative model to just for the imagination purpose, so that we don't have the actual industry images as we are proposing this design. So, and we haven't done experiment. That's why we have created it using here. Here are the references of two papers which we have required for our entire ideation and final implementation, and not implementation, creating the solution. So, thank you.